Integration is a method of adding values on a large scale where we cannot perform journal addition operation. But there are multiple methods of integration which are used in mathematics to integrate the functions. There are different integration methods that are used to find an integral of some function which is easier to evaluate the original integral. So let us discuss the different methods of integration like integration by substitution, integration by parts. In the previous lecture, I discussed integration by substitution method for indefinite integrals. Now moving towards integration by substitution method for definite integrals. The definite integrals, there are basically two methods to evaluate a definite integral by substitution. Now, method one is basically to compute the indefinite integrals first and then use the evaluation or the fundamental theorem of that. And second way is to use the substitution rule for definite integrals. So the advantage of second method is that we do not need to undo the substitution. So in the second method, we compute the definite integrals directly, adjusting the limit of integration after the substitution. So we will follow this theorem which says that if y is equals to g of x is a differentiable function whose range is an interval I and the function is continuous on the interval I, then integral from a to b f of g of x into g dash of x dx is equals to integral g of a to g of b f of u du. Now let's apply the previous concept which I discussed here. Integral, evaluate this definite integral, integral 0 to 2 x into x square plus 1 whole cube dx. Let u equals to x square plus 1. Taking its derivative, I get du equals to 2x dx. Now x dx is the part of the integral. The extra term is 2. Taking this extra term on the left side, I get 1 by 2 du equals to x dx. Now, these are the limits for variable x. As I have changed the variable x to the variable u, then I need the limits for u. Now, how can I get the limits for the variable u? How can I get the new limits? I'll substitute the value of x here. Substituting value of x here in this expression, I'll get the value of u. So, when x is 0, when x is 0, value of u is 1. When x is 2, that means 2 square plus 1, 5. When x is 2, value of u is 5. So these are the new limits. When x is 0, value of u is 1. When x is 2, value of u is 5. Substituting the value lower limit and upper limit here, I am getting u cube du. Taking the integral of u cube, it's u4 by 4. Applying the limit, upper limit minus lower limit, I get the answer. Now this answer is a particular number because I told you in the previous lecture that whenever I'll deal with a definite integral, there will be no constant of integration and I'll get a specific number. But whenever I'll talk about the indefinite integral, At the end, I'll get a function of variable x plus the constant of integration. Now comes another example. Evaluate integral 0 to pi by 4 cos of pi minus x dx. Now let u equals to pi minus x. Taking its derivative, du equals to minus dx. Dx is the part of the integrand, so substitution is okay. Now changing the limits of integration, if x is 0, value of u is pi. If x is pi by 4, value of u is pi minus pi by 4, that is 3 pi by 4. So these are the new limits of the new variable u. Replacing the old limits with the new one, I get pi to 3 pi by 4 cos of u into minus du. So taking minus sign out of the integral, cos of u du, integral of cos u, that is sine u, upper limit minus lower limit, I am getting a number. This example is the same as previous one. Evaluate integral 0 to pi by 8 sine 5 2x cos 2x dx. Now I select u equals to sine 2x. Taking the derivative of sine 2x, I get 2 cos 2x dx. Cos 2x dx is the part of the integrand. I'll move the extra terms to the left side, so the left side becomes 1 by 2 du, right side is cos 2x dx. Now changing the limits of integration, substitute the value of x equals to 0 here in this expression. Sine of 0 is 0, so if x is 0, u is also 0. If x is pi by 8, the value of u is 1 by under the radical 2. Now replacing the old limits with the new ones and doing the substitution, I get u raised to the power 5 du, and 1 by 2 is constant, so it is out of the integral. Taking the integral of u raised to the power 5, it's u raised to the power 6 by 6. Substituting the limits, upper limit minus lower limit, I'm getting 1 by 96. Now comes another theorem. In chapter 1, I discussed function can be an even one and it can be an odd one. So let f be a function which is continuous on a symmetric interval a to b, minus a to plus a. If function is even, then integral minus a to a f of x dx is equals to 2 times 0 to a f of x dx, and if f is odd, then integral minus a to a f of x dx is 0. In simple words, I can say this, that if the area under an even function over a symmetric interval can be calculated by doubling the area over the positive x-axis, and for an odd function the integral over a symmetric interval is equals to 0 because half the area is negative. So applying this concept on this function, this is a function. Now check whether this function is an even function or odd function. So replace x by minus x. If replacing x by minus x, you get the same function again, then it means the function is an even function. And if it is equals to minus f of x, it means the function is odd. So we can see that the interval is symmetric as it is from minus a to plus a, and the function is even. If I replace x by minus x, I get this function back. So this function is even on the symmetric interval minus 2 to 2. So instead of solving this function on the interval minus 2 to plus 2, I can solve it on the positive x-axis 0 to 2, and multiplying it with 2. So by doing this, I have to do less calculations. So the answer is 232 by 15. In Introduction of Integration, we developed the concept of definite integrals to calculate area below a curve on given interval. In this section, we expand that idea to calculate the area of more complex regions. We start by finding the area between the two curves that are functions of x, beginning with simple case in which one function value is always greater than the other. Well, we are going to look at finding the area between the two curves that are actually two cases that we are going to be looking at. So in the first case, we want to determine the area between the two curves y is equal to f of x and y is equals to g of x on the interval a to b. And we are also going to assume that f of x is greater than equals to g of x. So take a look at the following sketch to get an idea of what we are initially going to look at. So A is uh, area is integral a to b f of x minus g of x dx, and the second case is it's almost identical to the first one. Here we are going to determine the area between the curves uh, x is equals to f of y and x is equals to g of y on the interval c to d, with f of y is greater than equals to g of y. So to find the area between the curves, you should first find out where the curves meet, which determines the endpoints of the integration, and you can then divide the area into vertical or horizontal strips and then integrate it. So there are two kind of area problems, first area problem and second area problems, as function can be written as y is equals to f of x, or it can be written as x is equals to f of y. So suppose that f and g are continuous functions on a closed interval ab, and the first function is greater than equals to the second function on this closed interval. This means that y is equals to f of x function lies above the curve y is equals to g of x. So f of x is lying above g of x, and that the 2 points can touch but they cannot cross. But if we have to find the area bounded above by y is equals to f of x and below by y is equals to g of x, or by this, or the sides by the line x is equals to a and x is equals to b, then area under f area can be calculated by area under f minus area under g, or we can say that area is equal to integral a to b f of x minus g of x dx. Now we can also say this, that if f and g are continuous functions on the interval a to b and f of x is greater than equals to g of x for all x in the closed interval ab, then area of the region bounded above by y is equals to f of x and bounded below by g of x, on the left by line x is equals to a and on the right by the line x equals to b, the area can be written as area is equals to integral a to b f of x minus g of x dx. Now here is a very simple example that find the area of the region bounded above by y is equals to x plus 6 and bounded below by y is equals to x square and bounded on the sides by the lines x is equals to 0 and x is equals to 2. Now first see that what kind of problem this is. Is this a first area problem or the second area problem? If both the functions are in the form of y is equals to f of x, this means then that this is the first area problem. So you have to do upper function minus lower function, or top function minus bottom function, you can say. So here it's clearly stated that which function is above, which is below. So above function minus below function. This means x plus 6 minus x squared dx. And the limits are from 0 to 2. So integrate this expression, you get the area between the curves. But life is not simple every time. So in the next question, you have to find the area of a region that is enclosed between the curves y is equals to x squared and y is equals to x plus 6. Now here you don't know the limits. So you have to find the limits, and then you have to check which function is above and which is below. So you have to sketch the graph also. Now, as both of the functions are in the form of y is equals to f of x, so what we can do is we can equate them. Why we are equating them? To find the limits of integration. So equate them, solve them. We get two values. X is equals to minus 2 and y equals to x equals to minus 2 and x equals to 3. This is a mistake. It's x, not y. So the lower limit is minus 2, the upper limit is 3. What is the upper function? Upper function is x plus 6, as it is the equation of a line which is 6 units up, and this is the equation of a parabola. So this is the upper function, this is the lower function. So upper function minus lower function, you just integrate the expression. This is the answer of the expression after integration, and after applying the upper limit minus lower limit, I'm getting the area which is 125 by 6. Now here is the second area problem, that if the function is in the form of x is equals to f of y, both of the functions are in the form of x equals to f of y, then what we will do is, there one function will be on the left, other one will be on the right. So what we have to do is we have to subtract the left function from the right. That means right minus left. In the first area problem, I was doing upper function minus lower function. In the second area problem, where x is equals to f of y, I'll do right function minus left function. So suppose that w and v are continuous functions of y on a closed interval c to d, and the right function is greater than equals to the left function for the closed interval. The curve x is equals to w of y lies to the right of the curve. It's on the right and this is on the left. Then how can you find the area between the two curves, as they are bounded by the lines y equals to d and y equals to c? You can find the area between the curves as right function minus left function integrated over the interval c to d. Here is another example of first area problem. After discussing this, I'll move to the second area problem example. Okay, determine the area enclosed by y equals to sine x and y equals to cos x on the interval 0 to 2 pi. Now you have to find the point of intersection, as both the functions are in terms of x. So y is equals to f of x. So equate them. After equating them, I am getting this value. So this is the sketch of the two curves. The interval is 0 to 2 pi, and we can see clearly that the function is not behaving the same on all intervals. If this function is on the top, cos x is on the top and sine is um, at the bottom in this interval, then you can see that in this interval sine function is on the top and cos is at the bottom. So the function is changing. So the top curves and the bottom curves are changing at the intersection points. Okay, so Now what we have to do is we have to find out the regions. So the top region changes at pi by 4 and 5 pi by 4. Thus we need to split the area up into three regions. First region is 0 to pi by 4, other one is pi by 4 to 5 pi by 4, and the third one is 5 pi by 4 to 2 pi. As this is the whole interval, I have divided this interval at the points of intersection. So these are the points of intersection, and breaking the interval at the point of intersection, I am getting the three regions, three sub-regions. So just check which function is at the top, which is at the bottom. So in interval 0 to pi by 4, cos function is the upper function while sine function is the lower function. So I'm doing cos x minus sine x. Thus, now the interval is pi by 4 to 5 pi by 4. Now the upper function is sine and the lower function is cos, so it's sine minus cos. Then from the interval 5 pi by 4 to 2 pi, the upper function is cos x and the lower function is sine x. So after integrating the expression and applying the limits, I am getting this value, 4 under the radical 2. Now this is an example on the second area problem. Determine the area enclosed by x equals to y square and x equals to 8. Now you can see clearly both functions are in terms of y. This means that this is the second area problem. So first find out the points of intersection by equating these two terms. Y square equals to 8. Value of y is plus minus 2 under the radical 2. Now sketching the two curves, x equals to y square is like this and x equals to 8 is a vertical line. You have to find the area between these two curves. So the lower limit is minus 2 under the radical 2 and the upper limit is 2 under the radical 2. The right curve is 8. The left curve is y square. So the function is 8 minus y square. Integrating 8 minus y square, I get 8y minus y cube by 3. Applying the limits, upper limit minus lower limit, I get 64 under the radical 2 by 3. Now, here in question number 96, you have to find the area of a triangular region in the first quadrant, bounded on the left by y-axis, bounded on the left by y-axis, bounded on the right by the curves sine x and cos x. Okay, so as both functions are in terms of x, so we can compare them to find the limits of integration. So comparing them, I get x equals to pi by 4. So the point of intersection is pi by 4. The lower limit is 0, upper limit is pi by 4. Now you have to find the area of this region. Why? Because in question it's written that you have to find the area of a triangular region in the first quadrant that is bounded on the left by the axis and on the right by the curves sine x and cos x. So this is the area. So as this is the first area problem, so this is upper function minus lower. So upper function is cos x, the lower one is sine x. So cos x minus sine x integrated over the interval 0 to pi by 4, we get the answer under the radical 2 minus 1. So this is how you solve the area problems. Okay, so after listening to this audio, you can now solve the questions of exercise 5.6 and further more questions on the topics of area between the curves and definite integral substitution.